Buenos días. Buenos días a todos, a todas. Gracias por su presencia en este evento, en esta conferencia. Voy a presentarles a nuestro ponente del día de hoy. Me están poniendo ahorita la imagen del cartel para que podamos ir viendo su semblanza. La presentación va a ser en inglés. De todos modos, si alguien quiere hacer una pregunta, lo puede hacer en inglés con toda libertad. Si necesitan que les ayudemos a traducir, pueden hacer su pregunta en español y con gusto pues les apoyamos. Bueno, en lo que nos ponen el cartel, ahí está. Muchas gracias. Pues quiero presentarles a Andrew W. Taylor. Él es asociado de KPFF actualmente, es presidente del prestigioso Comité ACI 318, que desarrolla la próxima edición del Código de Construcción en concreto para 2025. También es miembro de numerosos comités técnicos a nivel local y nacional en los Estados Unidos. Las especialidades de Andrew incluyen el diseño de estructuras con sistemas de protección sísmica, como aislamiento de base y disipación sísmica, así como la medición, el análisis y el diseño de sistemas con vibraciones. También es especialista en el diseño sísmico de estructuras de concreto reforzado, obviamente, y su experiencia profesional abarca 32 años de investigación y práctica profesional en ingeniería estructural, incluidos 7 años trabajando en el Building and Fire Research Laboratory del National Institute of Standards and Technology, NIST. Pues ayúdenme por favor a darle la bienvenida al Dr. Taylor. Thank you very much, Taylor.
So to advance is,
Do you need a pointer?
no, just do this, just
Just
touch.
do this.
Oh, okay.
Yes.
Okay, perfect. Okay, thank you. Thank you for inviting me. Yeah, oh, do I need, thank you. Thank you very much for that nice introduction, and thank you for coming this morning. I apologize that I don't speak any Spanish, so I will be presenting in English only. But of course, if you have any questions, if I use English terms that are not clear, please ask me. I'll do my best to explain. So I came here to participate in the seismic conference in Puebla, and while I'm here, I was invited very kindly to present a seminar this morning, and I proposed to give a seminar not on concrete, which is, of course, what I'm perhaps best known for my activities with ACI and the ACI 318 building code, but to give a seminar on seismic isolation and the very current topic of seismic isolation of buildings in Turkey. And so I was, my proposal was accepted, and I didn't know that there was such a strong interest in isolation in this department. So I'm glad that there is, and I'll be speaking about the Turkey earthquake and the behavior of base isolated hospitals. Now you may wonder why only hospitals. It's because in the area affected by the earthquakes, the base isolated buildings, as far as we know, were only hospitals. So all base isolated buildings that were affected by the earthquakes were hospitals. So this is why I'm discussing hospitals. So I first want to begin, of course, I'm sure you have all seen a lot of information about the Turkey earthquake, so I won't spend much time on that. But I was very interested, of course, in understanding the behavior of seismically isolated buildings after the earthquake. And I have tried to make inquiries and get information as best that I can, but of course, things are still very, still a very extreme emergency in Turkey. And so information I get is preliminary. I know that later we will receive more detailed information, but I just want to say that the information I have here is maybe preliminary, but it's useful and instructive to understand how hospitals behaved in this earthquake that were base isolated. So we all know there were two main events. The first earthquake was 7.8 magnitude, and the second, about 9 hours later, was 7.5 magnitude, as shown on this map. And we've also seen the tremendous tragedy, the results of structural collapses such as this one. I don't need to say any more about that other than it's very sad. And of course, we as structural engineers have a great responsibility to prevent scenes like this. In the first earthquake, the magnitude 7.8, if you focus on looking at the red, the dark red and dark red triangles, here, these ones, these are centimeters per second squared. So between 100 and 300, or 0.1 and 0.3 G, and even greater than 0.3 G, we see there were many instrumented locations that measured these very high accelerations. And if we look at the second event, this magnitude 7.5 event, we see also many red triangles greater than, in the range of 100 to 300 centimeters per second or greater. So this gives us an idea of how extreme the event was. And of course, I was very interested to learn how did isolated buildings behave in this extreme event. These are a lot of numbers from different seismograph recording stations. I just wanted to point out this is these are for the 10 closest recording stations to the main event, the first event. And we see numbers here, like these are peak ground acceleration, north-south direction, peak ground acceleration, east-west direction, and peak ground acceleration, the up-down or vertical direction. And I want to draw your attention particularly to this number here, 1.3 G horizontal acceleration, 0.9 G horizontal acceleration, and 2/3 or 0.675 G vertical acceleration. Here we even have, in one instance, a vertical acceleration greater than 1 G. In the second event, we see numbers not quite as high, but still very, very large. For instance, in the north-south direction, we have accelerations as high as 450 centimeters per second squared, and 325 or 520 here. And up down again, we have quite high numbers, 0.43 G vertical, and so on. So this is just to show that we are dealing with a very, very severe series of events. I'm only going to show two acceleration response spectra here, but again, they illustrate how this event compares to actually the Turkish building code, the 2019 Turkish building code. The green line is the event with a probability, mean probability of recurrence interval of 475 years, and the red line is for 2,475 years. We usually call this the 500-year earthquake and the 2,500-year earthquake. These are the design spectra that are for the 2,500-year event and also for the 475-year event. We see that particularly out at long periods, greater than maybe 1 second, or even as low as 0.5 second period, that these measurements exceeded even the greater, larger, most extreme design event that was considered. Looking at one more example of a spectrum, again, we see that these recorded ground motions exceeded by a large margin the design spectra. And these are very well-developed code design spectra. We just have a very extreme earthquake that that occurred, which was beyond even the design spectra. Finally, some spectra here that I just want to show for the purpose of comparison. These again are acceleration response spectra. This is at one station, at several stations. We have, I think maybe there's 1, 2, 3, 4, 5, 6, 7, 8, 10 recordings here. And then on top of that, I have some other lines which I'll describe in a moment. But these 10 recordings show that, for instance, some motions had very high horizontal accelerations out at periods as high as 2.5 seconds. And in the other direction, this is north-south, east-west, we see again very high response out around 2 seconds. Now this may look somewhat familiar to you because of the basin or geologic effects in Mexico City, where you have natural periods of the site are out further than you would normally have for a more competent soil. And so what we see here is a response at long periods, which is somewhat unusual. I plotted on this plot also 3 design code plots. These are for the US code. So for American Society of Civil Engineers, ASCE code 7, 2022, also for ASCE 7, 2016. Site class D is an average, a firm soil, not the best, but still a good soil condition. And site class C is very good soil condition. Site class E is almost the worst possible soil condition. We see that for the Seattle area, of course I'm from Seattle, so I plotted these for Seattle. The design spectra in the United States, which are the blue and the red and the green, also fall below the actual recorded motions by significant amounts in some cases. Site class E is a very, very soft site, and the design spectrum is quite high, especially out at long periods. Even so, these recorded motions greatly exceeded the US design spectrum, at least in the Seattle area. Okay, so moving on from the ground motions, this is the areas damaged, which received the highest damage. This map from the New York Times, but we see the worst ground shaking and the worst damage was in this area, but still the area of influence of the earthquake extended far out, perhaps at least a 200-kilometer radius from those epicenters. So before we look at the behavior of base-isolated hospitals, it is interesting to look at the behavior of non-base isolated or fixed-base hospitals. And a very early report came back from the Earthquake Engineering Research Institute reconnaissance team stating that generally hospitals, at least newer hospitals, behaved well in the earthquake structurally, but many of them were observed to be non-functional because of non-structural damage. And non-structural damage results from high accelerations in the building and from high distortions or drift in the building. And so many hospitals were closed because of non-structural damage. And in at least one case, the damage was determined to be non-structural, but it was very visible, and the people working in the hospital would not return into the hospital, even though it was safe from a structural point of view, because of their concern about the non-structural damage. Immediately after the earthquake, more than 15 hospitals, and perhaps many more than 15, but at least 15 were taken out of service. They were non-functional. In one province, only one hospital remained functional. There were also reports of hospitals that suffered major structural damage. So although most did well, some were damaged structurally quite severely, and at least 2 hospitals collapsed. This is a hospital in Antakya. It actually split in 2, and then half of the building collapsed, as you see in this photograph, and is being demolished. So this is an example of a hospital that behaved very poorly structurally in the earthquakes. And very often hospitals were abandoned, and temporary or field hospitals were established out in the parking lots. This is the field hospital at Hate, and the actual hospital, which is empty, it can be seen behind the tents here. This is another view of the same hospital. This is a team, an overseas team who has come to assist with the earthquake aftermath. But again, this is the hospital which is non-functional and is replaced by the tents here. So this is a very important and concerning problem with hospitals, is non-structural damage causing the hospitals to be abandoned. Now let's look at isolated hospitals. There was a rule established in 2013 by the Turkish Ministry of Health that required essentially most hospitals, large hospitals, over 100 beds, which is not a very large hospital, but in the seismic zones 1 and 2, which are the most severe seismic zones in Turkey, to be base isolated. My understanding is today there are about 100 base isolated buildings total in Turkey, and that many of these are hospitals because of this ruling in 2013. In the region affected by the earthquake, there were 12 base isolated hospitals within about 200-kilometer radius. A reconnaissance team from the Turkish Association for Seismic Isolation, or TASI, was able to visit all 12 of these base isolated hospitals within a few days after the earthquake. So some of the information I have comes from that organization. Here's a map showing the base isolated hospitals in a region. This circle is at 100 kilometers and 200 kilometers. And we see the red labels are the 12 hospitals that were base isolated and were affected by strong ground shaking. Looking for sources of information, I found one news source that reported that at the time of the earthquake, there were actually 3 base isolated hospitals that were under construction in the affected area. And these were government-owned facilities at 3 locations, and despite being only partially constructed, so in the middle of construction, they were reported to behave very well, even though they weren't complete. One example is the Kahramanmaraş Hospital, which we'll see here in a moment. This was under construction. You can see the base isolation system at the lowest level that is under construction. This is a friction pendulum system, or a dish system with 2 dishes, one below and one above. This portion of the hospital actually performed very well structurally during the earthquake, even though it's only about less than half of the hospital is completed. So that was encouraging. even though this hospital was under construction at the time of the earthquake, with the isolators locked for construction. So during construction, there are plates on the isolators that are there to hold the isolator in position. These plates broke away due to the ground motions, and the building did very well. But perhaps equally as interesting is that a 2010 portion of this hospital was constructed 12 years ago. Fixed base portion of the hospital did not perform well, and it was immediately next door. So here we have a case of a base isolated under construction hospital, and then a completed hospital that's not base isolated, and it performed very well and performed very poorly, the fixed base hospital, and had to be abandoned. So this is a very interesting sort of observation of a base isolated and non-base isolated portions of a hospital being tested by the same earthquake. So you may wonder, naturally, the question arises, well, how much did the base isolated hospitals move? What was their range of motion? They were, according to the early report from the Turkish Seismic Isolation Organization, the maximum seismic movement ranged from quite small, 1 to 2 centimeters, up to as high as 16 centimeters. The photograph shown here is actually from Japan. It's beneath a building in the Sendai, Japan area after the 2011 earthquake. And this is a device that records the path of motion of the isolated structure above relative to the non-isolated structure or the foundation below. And it creates a scratch on the plate. And you can see in this case in Japan that the displacement was about 23 centimeters. This is the maximum displacement here. So when these types of very simple devices are in place, then we can at least determine the main directionality of movement and the maximum displacement. We can't always determine the details of the motion at low displacements, but we can at least see what the maximum is. Now, the question has come up, because of the extreme response spectra from this event, some of them showing displacement spectra out greater than 1, even approaching 2 meters of spectral displacement at longer periods. Why did the hospitals exhibit only 2 to 16 centimeters of displacement? I don't think that is fully understood yet, but I would point out that when we look at spectra, such as the ones I showed earlier, they're created for 5% linear damping. It's just sort of standard, it's implicit, not always stated explicitly. But the damping provided by a seismic isolation system may be considerably greater than 5%. And so comparing the response to a 5% damp spectrum is not actually a direct, correct interpretation of the response. You should probably compare the response, the observed response, to maybe 15 or 20% damp spectrum. So this will all be understood eventually, but I just wanted to point out that this level of motion at first doesn't seem consistent with the actual the spectra that were recorded. What kinds of devices were used? In all 12 hospitals, they were sliding devices like this. There are isolated hospitals in Turkey on rubber isolation bearings. It happens that in this event, all of the hospitals were either with a double surface, concave surface, or a double friction pendulum bearing, or I think 1 or 2 of them had triple friction pendulum bearings like this. So these are the type of devices that were tested in these earthquakes. So also in the news, there was a story on the 13th, so only about 7 days after the earthquake, reporting that 4 base isolated hospitals performed extremely well. And according to the news report, they did not suffer even the slightest damage thanks to the seismic isolation devices placed in their columns. And they were effective at treating earthquake injury victims. I think it's interesting that this is a general public news report. This isn't an engineering investigation or an engineering society's assessment. This is in the general newspaper, a local newspaper in Turkey, a few days after the earthquake. So this is in the consciousness of people in Turkey that seismic isolation is an effective earthquake damage preventative measure. So we know some information now, which I've presented. It would be nice to get more information, and I think we will. Eventually, I hope we'll see more detailed inspection reports of the 12 isolated hospitals that I showed earlier on the map. We'll see maybe a little better information we'll see at one of the hospitals did have instrumentation within the building. So we'll actually see recorded earthquake response of the isolated hospital. But also we will see ground motion data from nearby measurement locations. We all have already seen much of that much of that has been processed and released, but we may be looking more closely at comparing the behavior of for the hospitals that did not have instrumentation, of comparing their response to the recorded ground motions nearby. And then I hope eventually, and I'm sure we will, see a systematic study of the earthquake response of fixed base and isolated structures following this earthquake. So this is what I hope for the future. Now I want to shift gears here quite a bit. I wanted to show you an actual seismically isolated hospital project. This is one that I was involved with in Taiwan, but I thought you might be interested in seeing, sort of looking inside an actual design, engineering design of a seismically isolated hospital. So I just want to show a few slides about this in case you're interested in a real world example. So I was responsible for the design of the seismic isolation system. The superstructure, we were involved in the design, but the main design and responsibility was by a local firm, the Taiwan Engineering Consulting Group in Taipei. Architect was C.C. Xu, also in Taipei, and the facility is owned by a Buddhist relief charitable organization, the Tzu Chi Foundation. This is a picture of the completed facility, 1,200 beds, very large floor area, 167,000 square meters. At the time that this was completed, it was the largest base isolated hospital by area in the world. However, several hospitals in Turkey are larger than this. Very heavy structure, you can see, 285,000 tons. The main structural system is what is called in Taiwan and in Japan steel reinforced concrete, which I know that is used sometimes here in Mexico, which is a steel gravity supporting frame surrounded by each element surrounded by reinforced concrete. So it's a combination of a full steel structure and a full reinforced concrete structure. So and then the column grid, the spacing of columns was typically 8 meters by 8 meters. This is the location, which was the most challenging thing. In 1999, there was a major earthquake in Taiwan called the Chichi earthquake. It ruptured the Chalongpu Fault, and here's the fault, and here is the hospital, 400 meters from where that fault ruptured. At very near the location of the hospital, the Chalongpu Fault had a uplift, a step of 3 meters. So very severe conditions and a very challenging location to put a hospital that is intended to provide emergency relief. So of course base isolation was selected. The ground motions that we were designing for were from the Chi earthquake, the nearby motions recorded on the near the Chalongpu Fault, at which was only 400 meters away. But the ground motions from the Chi earthquake contained strong pulses of velocity. So you see here is a record. This is velocity versus time. You see this large pulse, which is not unusual for a recorded motion near a fault, a ruptured fault, sometimes called near fault effects or velocity pulse effects. As the rupture propagates along the fault, it's preceded by these very large velocity pulses. So because we have high velocities in our design criteria, we also incorporated dampers. In Japan and Taiwan, these are referred to as oil dampers because they contain oil. We would refer to them as technically as fluid viscous dampers, but they're also called hydraulic dampers or shock absorbers, just like you would have in a car. It's a piston with oil, and this end is connected to the ground, and this end is connected to the superstructure. These were very large dampers with a maximum design force of 175 tons. They were nonlinear dampers. The damping exponent here, alpha, was not 1, but was 0.4. And these helped control those very strong velocity pulses. Here's the system altogether. Consists of rubber bearings in this case with a lead core to provide additional damping. And then we have even further damping, viscous damping through these, this type of damper. There were 325 lead rubber bearings, sometimes called LRB, and 88 of the hydraulic or fluid viscous dampers. These were arranged, this is a plan view looking down. Each red dot is a seismic isolation bearing, a rubber bearing, and each green V shape represents 2 of those hydraulic dampers arranged at 90 degrees to one another. So there's a total of 88 of those dampers around the perimeter of the base. This is what the actual construction site looks like. You can see here the isolators in place. And there's also around the perimeter, there are columns and hardware for connecting the dampers between the superstructure and the substructure. This is the ETABS model. We performed a nonlinear time history analysis. The only nonlinear elements in the analysis were the isolation devices. The superstructure remained elastic, and we verified that during our analysis. Here's just a summary of the base isolation bearings. There were 6 types. Actually, there were 5 types, varying in diameter between 1 meter and 1.5 meter. These are their capacity, vertical load carrying capacities in tons, and this is the number of bearings of each type. For some very heavy loads, we put together 4 1 meter diameter isolators in a group to support very heavy, as much as 4,000 tons axial load. Here I am in front of some of these dampers, which again, they had their total capacity, I think, was around 300 tons force capacity. This is at the manufacturing plant actually in New York. And these are some of the isolators installed. Here's a single isolator. Here is a group of 4 isolators with 1 single plate. Here you can see the layout. These steel columns or brackets are for connecting the dampers from the superstructure to the substructure. And here's, just for a sense of scale, here's one of the smaller isolators installed. In terms of performance, the peak ground acceleration for design was for the 500-year earthquake was about 0.4 G, and for the 2,500-year earthquake, the peak ground acceleration was about 0.5 G. These are the displacements that we calculated for these two events, 0.34 meters and 0.6 meters. The base shear above the isolators was reduced, if you compare that to, for example, to the peak ground acceleration, we see that the base shear was 0.12 times the weight of the building, or a reduction of about 1/3, comparing this base shear above the isolator with potentially the peak ground acceleration. And then the interstory drift, which is very important for non-structural components, that is the displacement of one story relative to the other, was quite low, on the order of 0.2% of the height. So the displacement was only 0.002 times the height. And this is very important in a hospital because if you have a pipe that breaks or some other system that fails, it can completely close the hospital, as we saw in Turkey. So having these low interstory drift ratios is important. So that's the completed hospital. It's a very nice looking hospital. One thing I like about it is all of the patient rooms have windows that open and balconies so that patients aren't in a closed room. They can get fresh air. So if I'm ever in the hospital, I want to go here. So that's a completed project. And I'd like to end with one, I think, very interesting philosophy that I ran across in the Turkish building code, is this statement. And I think it is a good guide to us as researchers and practicing engineers about how to design structures for earthquakes. So it's in English, translated from Turkish, so I'll just explain. It says, due to the uncertainties in earthquake ground motion, structural modeling and structural element behaviors. So there's a lot of unknowns, not only in the ground motions, but also in how we model and how we understand the behavior of structural elements, as well as some approximations that we use in our approach to analysis and design. The basic rule of design under earthquakes is that the structural system should be as plain and simple as possible in order to ensure that the earthquake behavior of the building is predictable. So I subscribe to this philosophy. The simplest system is the best for earthquake resistance. I have seen some very, very complicated systems for base isolation, for example, that require gears and tracks and mechanical devices to maintain the orientation and movement of the building. The earthquake does not understand complicated mechanisms. It just breaks them. And you find pieces of these devices on the ground after the earthquake. But something very simple, like a sliding bearing or rubber bearing, or when it comes to the superstructure, trying to minimize irregularities and shifts in stiffness and so on, is always a benefit. So I just wanted to close with this little piece of philosophy that I found interesting and is actually stated as part of the building code in Turkey. So that's everything. Thank you very much. Oh, I should say that a copy of these slides will be available. I've given to the professor for if you want a copy. So you didn't need to take notes.
Thank you.
Okay, yeah.
¿Alguien tiene alguna pregunta? Any question?
Thank you for the presentation. It is actually a very technical question. You said that there were 26 based isolators that had the capacity of for type 1.
Yes.
I would like to know what caused that concentration of force, if there was some effect of torsional effects, and if it is so, how did you deal with it in the design?
Okay, good question. I will just go back to this photograph of the building. The places where there were very high loads were at the base of this tower. So this tower was 15 stories. It was very difficult to design the isolation system so that there was no tension. Yeah, but at the same time, that meant that the opposite, the compression, was very high. So the place where we needed those very high capacity groups of 4 bearings was underneath this footprint of this tower here. Yeah. Mm-hmm.
Another question?
Thank you, Andy. Going back to reinforced concrete structures, regarding these hospitals, I wonder if they were frames or based on walls, because some reports, for instance, the Middle East Technical University, they report that damage were mainly related to frame buildings rather than wall buildings. In fact, they report no collapses in number of wall buildings. So I don't know, what's your opinion on this? Especially because in Mexico, a common practice is using frames, reinforced frames.
Mm-hmm.
Unfortunately, we know good detailing because Chapter 18 is not mandatory here.
Yeah. Okay, good point. I didn't go into what the superstructure systems were for the base isolated hospitals, but I actually don't have that information. So I don't know if they were frame, lateral force resisting systems were moment frames, or if they were shear walls. I don't know. One sometimes challenge with base isolated buildings that have shear walls is that the overturning forces created by the shear walls are quite high, and unless you transfer those compression and tension couple out into nearby, structurally, you spread that out so that it's shared by a larger portion of the base isolation system, that can be very challenging. It's similar to what we had here. This is a frame building, this one here. It has not been subjected to a large earthquake, but it's very, very robust. These columns, some of the columns near the top are 1 meter square. So I trust the performance of this building. I don't know in Turkey what the comparison was. You mentioned the information from METU. That may be in general true in Turkey for whatever reasons, that frame buildings did not perform as well as shear wall buildings, but there's probably many reasons for that I don't understand. So I couldn't say. But with base isolation, it's sometimes difficult to deal with shear wall overturning locally. Yes?
And a question. In the design of hospitals, not only partitions become important, but hydraulic and air pipings and all that. Yeah. What has been your experience in the relation between you as a structural engineer and the mechanical engineer who is in charge of the design? Who does what? And to what extent that is because it works, because you have the mechanical engineer in your office, or how does that work? And the second is if these buildings are mandatorily instrumented.
Okay. I think, to kind of go backwards, I think that base isolated hospitals under new construction now in Turkey are required to be instrumented. I think, unfortunately, only one of the ones that is completed and was affected by the earthquakes had instrumentation. At least that's the information I have now. So in the U.S., there are varying rules, and there are in the national building, the model national code, there are requirements for instrumenting certain types of buildings. They aren't always followed. They are probably most often followed in California, especially with hospitals, where the authority that oversees the approval and design of hospitals is very much enforces that idea. Okay, so let's see. I started at the end. The middle of your question was mechanical engineers. Okay, so this is actually a very challenging issue in the U.S. with all performance-based seismic design, is how do we make sure that, we've done our job as structural engineers, how do we make sure that the rest of the building behaves? Because I think recent earthquakes in areas that are have been developed over a long period of time with building codes that recognize seismic design or seismic hazards as important, the observation has been that many problems occur with non-structural behavior, even if structural behavior is perfect. And we even saw that in this earthquake. In the US, we don't have a very good system or mechanism for collaboration between the structural engineer and the non-structural engineers. It's not just mechanical systems. Another very important one is the building exterior, the cladding system. Because in a hospital, especially if that fails, then you have issues with infection control because you don't control the air in the hospital anymore. So I would say it's a problem. I think the non-structural design rules for in the U.S. building codes have gotten much better in the last 10 to 20 years at explaining to the mechanical engineers and others what the requirements are. But having said that, there's still a long ways to go to get the mechanical and structural engineers talking. For instance, we don't have mechanical engineering in our office. We're structural and civil. So we don't have the opportunity to do that. But another thing is that, BIM modeling very often includes mechanical systems. So that might provide us an opportunity to have a structural review of mechanical systems and say, we think here there might be an interference or a problem with displacements or some other collision or whatever. So was that all the parts of your question? Yeah, okay.
We have one more question. I understood that on the analysis you get elastic behavior of the structure above the
Yes.
isolation. So I wonder if did you detail that as an ordinary frames or did you consider some more detailing?
Seismic detailing.
Yeah,
Yes.
thanks.
Good question. So in this particular project, the superstructure was designed by the local engineer in Taiwan, and I worked on the seismic isolation system. The local engineer voluntarily and at the direction of the building owner, asked for the superstructure to also be special, essentially special system, this steel reinforced concrete system, which is very ductile and strong and robust. So the owner wanted extra assurance that their structure would behave well, even if it is isolated, even together with very high-performance superstructure and isolation system. In the U.S., when we're designing the superstructure of a base-isolated building, we are required to provide what's called essentially elastic performance of the superstructure. This doesn't mean completely elastic. It means some inelastic behavior is permitted. So we need to provide, if you think of a simple intermediate and or ordinary intermediate and special superstructure design. Basically, in the U.S., it requires sort of an intermediate design. So there is some seismic detailing. It's not just a non-seismic structure on top of an isolation system, but it's not a special system on top. So the reason for that is there's great concern that if there's inelastic behavior permitted in the superstructure of an isolated building, that the period of the superstructure will become longer, and then the difference in period between the isolation system and the superstructure, they become closer together and the seismic isolation is less effective. So the idea is to ensure that the superstructure remains mainly elastic so that its dynamic properties don't change very much during the earthquake, and that the separation of periods between the superstructure and the isolation system remains significant. So, yeah.
Thank you. After the earthquake, I saw like a ground shaking with almost 1.9 G of horizontal acceleration and with about 7 G of spectral acceleration. But in your tables, I didn't show those values. So I wonder if you have any information of that very large record.
So the records that I showed were selected as the 10 closest to the area of the worst level of ground shaking, essentially the epicenter of the the first event, and then another table for the second event. At the time that table was assembled, there might not have been a complete processing of all the records. So I don't know any details about the records you're referring to. I've heard of them, but those weren't included in that table. But I don't really know any details about them.
I wonder if they removed that record because they think it's not reliable or something. But
I don't know. Okay. It takes some time after a major earthquake to agree upon what the valid, correct data is and to process it all. So I think we're still in that period of time.
Thank you for your presentation. From the fixed-base hospitals, where 15 of them were closed, and from the isolated buildings, how many of them were precast concrete? And if all the frames were moment frames, as we do here in Mexico, or were there a combination with non-moment resisting frames like sometimes in the United States?
I don't know the details of the superstructures of each of those 12 hospitals. It will be very interesting to find that out. We only have a small amount of information right now, and I've just pulled everything I could find. But obviously that information is available somewhere. And I think if we get more complete reporting of the behavior of the base isolated hospitals, that will include what the structural systems were. I don't know if there were any precast superstructures, which I'm guessing is your main interest. Yeah, so I don't know at this time.
¿Alguna otra pregunta? ¿No? Bueno, pues si no, pues démosle las gracias a Andy. Thank you very much, Andy.
Thank you. Thank you very much.
I have one certificate of appreciation in a small gift.
Ah, thank you. Thank you very much. We have photographers. Thank you. Thank you. Very good. Okay.
Muchas gracias a todos. Nos vemos pronto.
I wish I could make more conclusions, but I can present what the observations.